Hello everyone, I'm Ravit Pulyani and today I'm going to be presenting on the topic audio signals and filtering. So in this presentation I'm going to cover about audio signals and I'm going to demonstrate the filtering process through an audio file that I've recorded today, and I hope this presentation gives you a lot of insights. So without further ado, let's begin. So what are audio signals? Audio signals are representations of sound, typically as electrical or digital signals. They convey information about sound waves, which are variations in air pressure and are used to capture, manipulate, or reproduce sound. So, audio is something we listen to, we know it in the form of some waveform. It has a certain wavelength, it has a certain frequency attached to it, and it exists in mainly two forms, analog forms and digital forms, which we are going to see later. So any audio signal we see has three main components: its frequency, its amplitude, and its waveform. The number of cycles per second for a sound wave, it is called frequency. It is measured in hertz, and a lower frequency would result in a low pitch sound, and a higher frequency would result in a high pitch sound. And for us to hear anything, it should be between 20 Hz to 20 kHz. The amplitude refers to the strength or intensity. Louder amplitude means a louder sound, and a lower amplitude means a quieter sound. And the waveform, any audio signal has some sort of waveform attached to it, and different waveforms indicate different forms of sounds coming out of. Now we are going to contrast the differences in analog and digital signals. So the analog signals are like direct representations of the sound waves variations in air pressure over time. We see the analog signals as the sound it is. So there can be infinitely many values within given range of time intervals, and they are processed in the form of vinyl records and cassette tapes, like we used to do in vintage times. Some places do it even now. And the signals, on the other hand, are like discrete representation of sound. We obtain it from the analog signals by sampling at different time intervals. Digital signals are basically approximations to the analog signals, and they're processed as MP3 files, WAV files, digital audios in CDs and in DVDs. Today, I'm going to be processing a WAV file, which is a digital audio signal. Now, to get a digital audio file from an analog audio file, we need to perform three steps, which is sampling, quantization, and encoding. All this would give me a digital file, which I will store as a WAV file or an MP3 file. And to get back the original analog recording, what I'm going to use is a digital analog converter, which would play back the sound, sorry, in its analog form. So let's get into the process of digital conversion. First we have is sampling. Sampling is basically reading the audio file in different intervals of time, and the rate at which the analog signal is sampled is the sampling rate. To represent an analog signal, the sampling rate must be at least twice the highest frequency present in the signal. The highest frequency we are going to be representing as omega m, and the sampling rate as omega s. This is the Nyquist-Shannon theorem, and since I've already told you that humans can hear up to 20 kilohertz, the sampling rate is commonly used as 44.1 kilohertz to ensure high fidelity. So this is the something I wrote, something to explain you how sampling works. All we have to do is multiply two signals. One is I took a sample signal of minus sine t, and I'm going to multiply it with a train of impulses whose period is ts. And the result I get is a sample which somehow approximates to the original signal. And in the figure below, we have the Fourier domain, the Fourier transform of our original minus sine t signal. We call it x omega, and it is as follows. You can see the graph of x omega, and its omega m is 1. And in frequency domain, the train of impulses we saw in time domain, if we convert it into frequency domain, we get another train of impulses with time period of omega s, which is equal to 2 pi by ts. Now, using the correspondence relation, we can get the sampling rate in the frequency domain, which is something that looks like this. We saw one direct delta function at -1 and the other at 1, and now we see it periodically due to the convolution. And if this omega s was not greater than twice the omega m, we would see an overlap and our sampling would not be done properly. So it is necessary, and that was the Nyquist-Shannon theorem, that omega s is greater than twice of omega m. Now the second bit is quantization. Now that we have the sampled audio, we can quantize it to get this waveform, this particular type of waveform, this discrete digital signal, and the efficiency with which this operation is done uh, determines how close is our audio to the analog signal, how well it is being converted into digital form. So this shows that the level of quantization that we see is noise in the frequency domain. The bottom left graph shows that in the frequency domain, our analog signal would have looked like a square wave. But due to the quantization error, we see noise, which is represented by the orange line, and that is something that we don't need. So we would process this file to get rid of the noise. So now that we have our quantized version of our audio file, we would just encode it into binary form into zeros and ones to get a final digital file, and it is stored as an MP3 form or a WAV form. We would do all sorts of processes in it, and anything we want to do, we want to EQ it, we want to reverb, add some reverb, we want to add filters to it, we can all do it in our WAV file. So this is one WAV file that I created. This is my voice. This is something I recorded today. Hello, my name is Ravit. So the graph on the top left shows the variation of amplitude with time, and the graph on the bottom left shows the frequencies and their magnitude in the audio. You can see that my voice is a low frequency dominated voice. Low frequencies are quite prevalent in this audio. Hello, my name is. So now what we are going to do is that we are going to filter this very audio. And before that, let me introduce you to what filtering of audio signals really is. Filtering is basically altering the frequency content by emphasizing or suppressing certain frequency components. We can remove unwanted noise, enhance certain aspects of the signal, or extract useful information. We'll be focusing on four particular types of filters in this presentation, which is the low pass filter, high pass filter, band pass filter, and the band stop filter. So how is filtering done? You can choose two paths to filter your audio. One is in the time domain and the other is in the frequency domain. Today we would be discussing about the frequency domain as it would give us a direct understanding of how altering frequencies results in changing of voice. To apply filters, we'll first convert our time domain signal into frequency domain using Fourier transform. And the filter itself is represented as a transfer function, which is h omega. We just multiply our function in the frequency domain to this transfer function to get ourselves a filtered signal. This filtered signal is called y omega. So let's begin with the low pass filter. So low pass filter cuts the higher frequencies and allows the low frequency to pass. The cutoff frequency is the point where the filter begins to reduce the amplitude of higher frequencies. This is used in noise reduction. Any sort of noise, any sort of disturbance that we see, that we hear, is usually at high frequencies, and we need to cut them in order to get our audio to sound better. Also, any sort of hissing sound that I might say is at it is at higher frequencies, and it might just hurt your ear a little bit. So we need to get rid of that too. We get a smoothened audio once we apply the low pass filter. To demonstrate it, we can see on top left is my frequency domain, my original audio signal in the frequency domain, and on the top right is the transfer function. You can see the transfer function basically cuts off the higher frequencies, and if we multiply them, we get this particular waveform. This is my original audio.
Hello, my name is Ravit.
And this
Hello, my name is Ravit.
is the low pass audio. The low pass audio, you can see only lower frequencies are there. There are no higher frequencies, and the audio sounds a bit heavy and a bit smoothened.
Hello, my
So now the high pass filter, it does the inverse. It cuts off the lower frequencies, and we are able to hear the higher frequencies in the audio. So any sort of rumbling, any sort of humming is usually found at lower frequencies, and we don't want it in our audio sometimes. And also that any low frequency parts played by the instruments or in the vocals, we don't need that. So we need to apply a high pass filter in that case. This is again the original audio,
Hello, my name is Ravit.
and this
Hello, my name is Ravit.
is the high pass filter. You can see any heaviness is absent in the voice, any sound of wind is not there, and you can see why. I applied the high pass filter, which doesn't allow frequencies below this very mark to exist. So you can see the lower frequencies here are absent, and the rest of the audio is same as it is.
Hello, my name is Ravit.
So the band pass filter allows a specific band of frequencies to pass while attenuating frequencies outside of this range. So a band pass basically does both the things, cuts off the lower frequencies and the higher frequencies which are not needed. And this is very useful as we want one particular band of frequencies in our audio. So this is very much used in equalization and some musical instruments. Like if we need to apply certain filters in a number of instruments we are coordinating, we need certain band for certain musical instruments. This is the band pass filter. Let me show you the original audio.
Hello, my name is Ravit.
And now what I'll do, I'll cut off the frequencies below this 500 mark and cut off the frequencies beyond the 3000 mark. So all I'm left with is the frequencies in between, and it sounds like this.
Hello, my name is Ravit. Hello, My name
So a band stop filter, again, it cuts a band and removes the frequencies from it. And this is very useful in cases of feedback suppression, where, if we are coordinating certain entities producing sounds, uh, it might happen that a particular frequency is like ringing a lot and we need to remove it. So for that, we have the band stop filter. We can cut off the frequencies from this to this, and it is also used in medical applications. A notch filter is a narrow band stop filter that removes a very specific frequency or set of frequencies. It has medical applications and is used in ECGs and other biosignal processing to eliminate noise from power lines. So what I've done is I've removed frequencies from this 1000 mark to 2000 mark, and you can just see the comparison.
Hello, my name is Ravit. Hello, my name is Ravit.
So the frequencies from 1000 to 2000 are absent in the second audio.
Hello,
So the applications of audio filters, it is used in noise reduction. If there's any noise, any hissing sound, we can use the high pass filter and remove it. And we can use filtering in equalization. We can adjust the balance of different frequency components, and it is used in crossover in audio systems. So imagine a situation where different speakers are aligned in one particular orientation. So we might be needing to remove some frequencies and we need to filter it. And it is used in communication systems. Of course, we don't want any disturbance when we are talking to someone, and any interference is thus removed via filtering. And it is also used in sound design to create certain effects and make our sounds even better. So in conclusion, I can say that audio signal processing and filtering play a critical role in improving sound quality and clarity in various applications. The right choice of filters can dramatically improve noise reduction, signal enhancement, and the overall audio experience. So just remember that whenever you listen to any good music on Spotify or on YouTube, just remember there are millions of filters applied to it and it is heavily processed, and the good quality of music that reaches your ears is because of the audio filters. So here's me signing off. Hope this presentation gave you some insights on the topic, and thank you very much.